the organizers for giving me opportunity to talk here. I enjoyed this symposium and also every talk, and also enjoy every night. My title, the title of my talk is another form of the reciprocity law. Of Dedekind sum. Dedekind sum. This is a jointed work with Tadashi Ashikaga. Dedekind sum was first studied, of course, by Dedekind in 19th centuries for describing the transformation formula of Dedekind eta function. Dedekind eta function is defined as follows. Exponential かな。長くなっちゃう。For the element of the upper half plane, tau, eta t is defined as follows by infinitary products. どこだっけな。こっちだ。exponential. I'm sorry. Like this. So for each element of the SL2G, A, B, C, D, this is the element of the SL2D. There is a transformation formula, log eta tau, for log eta tau is equal to the log eta tau, どうだっけ plus little bit wrong, log CZ plus D over I plus like this. In fact, phi is the element of the real number, more precisely z over 3. The Dedekind gives the explicit formula for phi A theorem by Dedekind. Phi A is given, phi is given like this. A plus D, for positive C, for C, we call here, this is a fractional number, we call this Dedekind sum. Dedekind sum is given like this. There are some like this using the cotangent どこだっけな。Like this. Some people is familiar to the other formula for Dedekind sum, like this. This is the sum of fraction numbers, like this, using double bracket. CAR times CR, the sum of them. Where x is defined by as follows. The bracket x is the minimal integer not exceeding 2x minus 1/2 when when x belongs to the integer, but otherwise 0. So some people feel strange, the definition of this is double bracket, but of course, you can prove this is equal to this, of course. But to induce this formula from this, we use the Fourier expansion of cotangent, like this. Cotangent no. Sorry. そうすいませんね。コタンジェントの this is a Fourier expansion. Double bracket is appear here, like this. First, I would like to introduce our main theorem. Our main theorem is expressed formula to obtain the Dedekind sum by easy way. SAC is in fact equal to the like this. Sorry. From this formula, we obtain some elementary property for Dedekind sum, like this. And so we can assume that A is not greater than C by this property. So, so I must explain the notations. Ki are the integer which appears in continued fraction expansion, continued linear fraction of negative type, like this. And R is the length of their expansion. So, and A dash is a minimal positive integer satisfying this equation. A dash equal to 1 mod modulo C. Modulo C. Of course, this is a can be rewrite. There exists a positive integer CM2 plus 1, of course, in the by the assumption of minimality. M2, we can take M2 this region. This region. For after convenience, we introduce the. I would like to introduce some notations. Let N0 be C, and N1 be A, and Ni can be decided inductively as follows. As follows. Then N2 is equal to K1A minus C. Multiplying M2, we can obtain K1A minus M2 minus C M2. So using this we can write plus 1. So M2 is equal to the 1 modulo A. And M2, we can take M2 this region, so M2 is a minimal integer which satisfies these equations. Note that. To prove this main theorem, we use the geometric lemma by Matsumoto. First, Matsumoto and Montesinos. First.
Matsumoto? Who is Matsumoto?
Matsumoto. 何でした松本幸雄先生、幸雄松本。幸雄松本。こんなことを忘れるとしまうんですね。こう、だんだん日本語の講演が多くなってきます。Y、松本 and Montesinos。They prove, sorry. They prove this theorem. They prove this theorem by elementary number theory. But their motivation is from geometry. Geometry means the monodromy of the derivation of curves. So motivation is from motivation comes from geometry. Geometry means the monodromy, topological monodromy of degeneration of curves, family of curves. For after prove using this theorem, I would like to give another proof using the following theorem by maybe first Ishida. So let x dash is a germ of the quotient singularity of type AC, and let x tilde is a minimal resolution. A C over maybe A dash A delta. Oh, sorry, A dash. So, then the discrepancy is described as this: theorem 1 and theorem 2. It should be the well-known formula, maybe. By Masanori Ishida. This is proved by technique of toric Of course, this formula is explicit formula to obtain the Dedekind sum, but we want to claim that this is another form of the reciprocity law, because by elementary calculation we can obtain the reciprocity law from this formula. Reciprocity law is given by this as reciprocity law. Reciprocity law is SAC plus SCA is equal to like this. This law is proven by many peoples. So confer Rademacher, the books of the Rademacher Grosswald book. And Grosswald. One book. First, we want to prove that the reciprocity law can be induced from the main theorem. Reciprocity law. It is very easy, so I want to take a title. So, because SAC plus SCA is equal to SAC plus SK1 A minus N2 A by this. So the property of this and this, we calculate that SAC is equal to S minus S N2 A. Note that the definition of N2, the fractional expansion here is equal to L to A. So we use this formula twice. We can use this formula twice. This is a fast term, of course. And second, if the length of the expansion is less than this, so length is R minus 1, and here is the relation like this, so we can calculate this from that. Plus J equals to R, okay, J. So it only remains the K1 from these calculations, and R vanishes. So we can calculate like this. C square minus M2C, but by definition of M2, we know this, so this is equal to 1. This is equal to 1. So we can obtain this reciprocity law. So first, we prove my main theorem from this Matsumoto-Montesinos theorem using the reciprocity law. So this proof is not proof. This proof is not proof of the reciprocity law because to obtain this formula, we use this theorem and reciprocity law. But first, we prove our main theorem. We prove our main theorem. Theorem 1 plus reciprocity law induce the main theorem. For calculate this, we use the reciprocity law. This by similar calculation, we can calculate it like this. M2 A is equal to minus 4分の1 A plus AC plus 1 over AC, but A and C is equal to N0 and N1. So we can calculate like this using reciprocity law. Again, we apply the reciprocity law to this Dedekind sum. Reciprocity law. So we obtain the sorry. No. We have to calculate more because by definition we can calculate this more like this. Using these relations. So we apply the reciprocity law more. We obtain the equation like follows, as follows. K1 plus K2 and N0, N1 plus 1 over N1, N2. We calculate more, so finally we can obtain like this. Over C minus L1 plus the summation of the fraction in this integer appear, and by like this. But A and C is relatively prime, and this NR is equal to 1, and NR minus 1 is KR in fact. Is equal to 1, and this is equal to KR. So, more. Using the well-known formula like this, well-known formula, substituting this, we obtain the main term, in fact. I want to say again that this is not proof of the reciprocity law in this time, because to prove this main theorem, we use reciprocity law. So I would like to say that we reprove the reciprocity law. So we must avoid using reciprocity law. The second proof from this is given not using the reciprocity law, but using Hilsbeth-Zagier signature theorem. The next, we prove this formula from this without reciprocity law. The next is theorem 2 induce the main theorem. We need a very easy lemma. For any integer e, c, there exists a Riemann surface, algebraic curves over C, Riemann surface, and automorphism of sigma z. This is automorphism. Satisfying the period of the order of phi is equal to C. Phi followed by C is an identity with sigma z, and phi have a only fixed point. The number of fixed points is equal to R. C. And what point is the only fixed point? That means the fixed point of phi powered by I is equal to fixed phi. I equal 1, 2, C. And the action near fixed point is described as Ui is a neighborhood of Pi. Where Ui is a neighborhood of Pi. Of course, Pi is the center of Ui. The proof of lemma is very simple. Take a cyclic curve of degree C of P1 like this. Sigma z is equal to the given by these equations in the total space of the line boundary of P11, where x is an inhomogeneous coordinate of genus coordinate of P1. And the automorphism is given by covering transformations, of course. The automorphism is given by this. Covering transformation. We can easily check this property, of course. Sorry. Oh, sorry, C minus 1. We can construct this automorphism, in fact, directly using the topological method. So this is not proof of lemma, but first you prepare the C disk. This is a disk of C. C disk. And connecting the angle of this either C 2 pi over C, and connecting this region and this region by twisted ribbon. Twisted ribbon like this. Twisted ribbon. Twist. And their rotation around this axis gives this automorphism. In fact, so it's topological proof of the lemma. Because this is a curve with a boundary C disk with C boundary, and so the rotation is this rotation is this like this. So G is equal to the by Fluid's formula. We can calculate this. So we given the I'd like to begin the proof of the theorem, main theorem using theorem 2. We use this automorphism phi. Let M is a direct product of sigma z obtained here, and let the automorphism of M is defined by direct product of phi cross phi bar pi A. So we can consider the sorry. Phi is defined by phi cross phi A. Well, of course, we can consider the quotient map here, M dash, is equal to M quotient by the group generating by phi. Let's consider the minimal resolution of M. This is a resolution, minimal resolution of M. M dash. So this is a just only direct product, but this is this either vibration. This M dash has a vibration in this from the second projections. First projections like this. They has a singular fiber over P1 bar. P1 bar is the image of the quotient map of P1, like this. This is a rational curve, and this is a quotient singularity. Quotient singularity. The type AC. So the topology of M tilde is described as this. For this is a P1 or P1, and there exists a Hilbert-Young string, the length of equal to R, and these branches, they're the C branches, like this. So, and this surface has a quotient singularity type AC, only this type, and the number of singularity is equal to C square, because there is this is C square, because there is a critical point, C critical point, and each singular fiber there is a quotient singularity of types AC, the number of C. So the number is C. So by calculating the invariant of them, we can obtain their main theorem. This signature of M tilde is equal to the by Hilbert signature theorem, like this. But this is an Euler number of M tilde. So we calculate after this. And this is equal to this number, where there is a discrepancy of the resolutions. Sorry, the resolution map is there. And signature of M is equal to, of course, by using Hilbert's signature theorem, like this. But signature M dash is equal to signature M tilde plus C square R, because this is the contraction of Hilbert-Young string. The number of P1 is each branch is R, and there are the C branches, and there's a C singular fiber. So C and R and C. Of course, C2M is this, because this is just only direct product. And C2 M tilde is equal to the product of general fiber and the Euler number of base scheme and Euler contribution. There is a C singular fiber, and special fiber of the Euler number of the special fiber is calculated by RC plus 2, because this is the Euler number of the central curves, and this is a number of resolution graph. So n minus the Euler number of general fiber. This is the Euler number of singular fiber. And this is a Euler number of general fiber. So we can calculate this. To the C. Moreover, sorry, because this is nothing but a covering of degree R, finite covering. So we can calculate it. We can calculate it like this, and so let me calculate the signature defect of M and M prime. By Hilbert-Zagi's theorem, this is this can be like the information of the fixed point, like this. For this is a number of singular point, and Dedekind sum. There is no fixed curve from the construction. So we can calculate this like this using this property. But this square is a product of the number of singular fiber and Ishida's theorem. This. So we can calculate this from these numbers. I'd like to finish here. Thank you.